This four-dimensional continuum that we now know we live in has been confirmed 14 different ways to over 19 decimals. And it happens to include an insight that gets around many of the problems we encounter. So we want to talk a little bit about this peculiar dimension that you and I are in called time, the nature of time. Time, it turns out, let's talk about this first of all. There are atomic clocks located at the National Institute of Science and Standards and Technology in Boulder, Colorado, and also an identical clock at the Royal Observatory in Greenwich, England. These are atomic clocks. They're accurate. Both of these are accurate to better than 1 second per million years. So they're as accurate as we know how to make clocks. They're based on the natural resonance of cesium. I won't get into all that. That's not important. They're just very, very accurate clocks. But here's the dilemma. The one at Boulder ticks 5 microseconds a year faster than the identical clock at Greenwich. Every year they have to make an adjustment. Why? Which one's correct? Greenwich or Boulder? The Brits or our federal government? I didn't mean anything by that. That's all right. Well, the answer is they both are correct. You see, both are. The Boulder, Colorado is at 5,400 feet altitude, and Greenwich, England is at 80 feet of altitude. And the gravity is different at both places, which means the time, it's not the clock problem, the time itself is different at each place. The atomic clocks, if I had an atomic clock here on the platform, and I raised it 1 meter, it would speed up by 1 part in 10 to the 16th. Not a big deal, but it's measurable, predictable, and confirmable. In fact, they actually did this with an aircraft experiment back in 1971. They put an atomic clock on a plane going around the world eastward, and compared to one at the observatory, it lost 0.059 microseconds, or 59 nanoseconds. They did the same thing with one going westward around the world, and it gained 273 nanoseconds. Not a big deal, but it was exactly what the mathematicians had predicted because of all the factors involved, the motions and the gravity and so forth. I'll give you another example. This one's, I think, kind of fun. If you read a textbook in physics on this subject, you'll discover that they'll usually talk about these two imaginary, hypothetical astronauts. They're both born at the same instant. And we're going to send one of them to the nearest star. The nearest star to us happens to be Alpha Centauri. It's about roughly 4.5 light years away. If you look at the night sky, there actually is a star called Alpha Centauri, and that's the nearest one to us. And it is about 4.5 light years away. We're going to send one of these guys, we'll leave one here with us, we're going to send one of them to that star and back. Now, we're going to send them there at half the speed of light. This is obviously theoretical. And so that means that here on the Earth, it's going to take him, since 4.5 light years, going half the speed of light, it'll take him 9 years to get there, 9 years to come back. So he'll return in 18 years. Are we together so far? Okay. But what time is it on his clock? He's got a wristwatch around his wrist. What is it? Tally. And you can tell this by the Lorentz transformations, which I won't bore you through, but there is a correction factor. It turns out when he gets back, it'll only be 15 years and 7 months. In other words, he'll return 2 years and 5 months younger than his twin brother. And if that doesn't bother you, you weren't listening carefully. Two identical astronauts. One goes on the trip, one doesn't. The guy that gets back is younger than his twin. Man, that's interesting. Okay, to dramatize this further, let me go a step further. Let's assume we had sent him at 99.99% of the speed of light. Let's assume for the moment that'd be possible somehow. That would make the round trip 9 years on our calendar, but it would only take 33 days on his calendar. And so let's hope he bought some Microsoft stock on the way or something. But anyway, okay. See, time itself is a physical property. That's the point. We don't think of it that way. But time is a physical property, and it's not uniform. It varies with mass, acceleration, gravity, among other things. Well, here's the question then. Is God subject to mass or gravity?